All right, I'm going to go over our free fall notes. Make sure you have printed off the PDF of the printout fill-in-the-blank notes that go along with this. And yeah, let's get going. So before we really get into the nature of free fall, we are going to talk about a brief history of our understanding of free fall and how we came up with our thoughts. So we're going to start off with talking about some of the Greek philosophers. As you see, back in ancient Greece, the philosopher Aristotle believed that solid objects fell because they were made up of the element earth and were trying to get back under the air that was beneath them. Because back in ancient Greece, they had this understanding of the 5 elements, which were earth, water, wind or air, fire, and what's called the quintessence. I'm just going to write quint because I don't have enough room. And this was the order that they're supposed to be in. Earth on the bottom, then water, then wind, then fire, then the quintessence. And a rock would fall because it was made up mostly of earth, being a solid. And if you had a rock that was sitting up here and there's air underneath it, or water or whatever, the rock needed to get to down here below the wind or the air, and so it would just trying to get below, it would fall. And so that's why it would fall down, because it was trying to get in there. Now that was what Aristotle believed. That was what a lot of the ancient Greeks believed. And so it made sense based off of what they knew about the world. Now Aristotle reasoned that if an object was heavier, it was made up of more earth, and so if it would try to get to its below the air faster, so heavier object would fall faster than the lighter object. So he would say that a really, really big rock would fall faster than a really, really small rock and would hit the ground first because it was made up of more earth. It was trying to get there faster. Well, along comes Galileo, and he proved him wrong by dropping 2 rocks of different sizes from a tall building, and lo and behold, he found that the rocks hit the ground at the same time. So Galileo showed that Aristotle was not right. Aristotle said the big rock would fall faster and therefore hit the ground first. Galileo showed that, well, they wouldn't. But Galileo had a problem. He could explain what the rocks would do, but he couldn't explain why. And that, of course, is a problem in science, not being able to explain why. So along comes Newton and his understanding of gravity. Isaac Newton did something that Galileo couldn't do. He showed why Galileo's experiment did. And he did that through his discovery of the universal gravitation law, or the law of universal gravitation. It explained why Galileo got the results that he got. So in this, he found that gravity acts on all objects in Earth the same way. The key there is that we're on Earth. If you go to a different planet, it is slightly different. But on any given planet, any given location, gravity acts on all objects the same. It's indiscriminate of how it behaves. What this means for us is that all objects in free fall will fall the same way, no matter what. Now that was only part of what Newton figured out. Along with all of his other laws of motion, Newton also figured out that when things fall, they're falling because of a force, the force of gravity. And one thing that he learned with all of his experimentation and in his laws was that forces cause acceleration to happen. So Newton discovered that objects accelerate as they fall. That means they go faster and faster and faster as they fall. They don't just fall at a constant speed. The longer something is falling, the faster it's traveling when it hits the ground. Now because of this, we talk about something called the acceleration due to gravity. Gravity is a force, and gravity is causing it to accelerate, causing it to speed up as it falls. Any object that is falling is accelerating. Now this works only when an object is in free fall, and since we haven't actually defined what free fall is, let me do that. And this is not anywhere in your paper, so go ahead and write it down. Free fall is when an object is moving under the influence only of gravity. That's an A. So free fall, an object is moving under the influence of gravity only. And if I misspelled a word, sorry. So a couple of things that Newton told us about this acceleration due to gravity is that all objects fall with the same acceleration on Earth. Regardless of size, regardless of mass, on Earth, all objects fall with the same acceleration. Now this is an extremely important number in this class and in physics in general, and it's so important that it has its very own symbol. That symbol is little g. It's a lowercase g, and its value is a negative 9.8 meters per second squared. Now, don't get too messed up with that negative number there. It is negative, but that's principally because most of the time when we're dealing with g right now, we're going to be dealing with it in terms of kinematics. And in kinematics, direction matters, and gravity is always acting down, and that's why it's negative. There are certain situations where the gravity is not necessary to have the direction. We're dealing with things where we don't care about the direction, or like speed or energy and stuff like that. We don't care about the direction, so we're going to ignore the negative. If direction matters, though, g is going to be negative for this class. So what does this acceleration due to gravity actually mean? What it means here is every second your object's going 9.8 meters per second faster than it was before. So at time equals 0, it's not moving. 1 second later, it's falling at 9.8 meters per second. A second after that, so 2 seconds after you drop it, it's traveling at 9.6 meters per second. 3 seconds after that, it's traveling at 29.4 meters per second. So the longer it falls, the faster and faster and faster it goes. That is what acceleration due to gravity is all about. That's what little g tells us, that objects will accelerate at 9.8 meters per second squared as long as they're falling. Now, it is extremely important that you remember that little g is not gravity. It's an acceleration caused by gravity. That's why its unit is a meter per second squared, because it's an acceleration. Do not forget that this is not gravity. It is an acceleration. So again, little g is an acceleration. Gravity is a force. And Newton told us that forces cause accelerations, and that's why it's the acceleration caused by gravity. It is not gravity itself. I cannot stress enough how important it is that you understand that little g is not gravity. If I ask you what is the force of gravity and you tell me 9.8, I'm going to throw something at you, because no, it is not the force of gravity. It is the acceleration of gravity is 9.8. And no, I'm not really going to throw something at you. So we talked about little g as being a universe or a standard here on Earth, and it's a standard meaning it's always the same everywhere. That's what it means by standard. In a vacuum, which is the absence of matter. The problem is on Earth, a true vacuum does not exist in nature. We have to artificially create a vacuum. So out in space there's a vacuum, which means there's no matter anywhere, but most objects on Earth are always going to be falling in air, so we have to account for that. So if you think about it, if I have a big rock and a little tiny feather, that's a feather, and I drop them, we all know that when I drop them, the rock is going to fall and the feather is going to kind of flutter down, and so the rock will hit the ground first. Why does that happen? Well, let's look at another example. Since I didn't actually have a rock and a feather, I did it with a book and a piece of paper. So what you're actually going to see here is I have a book in one hand and a piece of paper in the other. I'm holding them at the same height, and I'm about to drop them, and we're going to see how they fall. If Newton was correct and all things fall at the same time, then obviously the book and the paper should hit the ground at the same time. So what happens? So So amazingly enough, the book hit the ground first, the paper fluttered down afterwards. Why did that happen? Why does the paper hit the ground after? We know Newton was right, but that's not what he said would happen. Gravity should act the same on both of them. So why does the paper hit after the book does? And the answer to that question is air resistance. A feather or a piece of paper interact with the air more than the rock or a book, and thus air slows down its acceleration considerably. See, the free fall is all about the acceleration. Free fall is all about acceleration. Remember, G is an acceleration. If I have air resistance, it's going to make that little g less. It's going to affect the way it falls and slow it down. So, in order to show that Newton was right, I have to remove air resistance. So let's see how I could possibly remove air resistance from this situation. Well, the paper and the book are both flowing, so let's remove the air resistance. And see what happens. Now it's going to drop, and the paper and the book fall together. This happens because, well, there's no longer any air resistance, and so gravity treats the paper just like it does the book, and they fall together. So we know that air resistance causes things to slow down, and because air resistance on an object, it will not accelerate forever. Without air resistance, an object will continue to accelerate as long as it is falling faster and faster and faster. But because of air resistance, they will not accelerate forever. They will reach a maximum speed. That maximum speed has a very special name. Terminal velocity, or terminal speed. That is that special name. So the actual definition, terminal velocity, is the maximum speed an object can reach when falling in air, and it's caused because of an increase in the air resistance as the object falls. As the object increases in speed, the effective air resistance becomes greater. The faster it falls, the more air resistance it has, and the slower it will accelerate. So it's still going to be accelerating up until it reaches its terminal velocity, but until then, its acceleration gets less and less. So basically, air resistance causes little g to get smaller and smaller and smaller until little g is 0. And this is all because of opposing forces. We'll talk about forces later in the year, but right now, gravity is pulling the object downward. So, big G, gravity pulling the object down, your air resistance is pushing up on the object. So at some point, those two forces will cancel each other out, and you will no longer accelerate, because we have to have a force to have an acceleration. Eventually those will cancel out and you will no longer accelerate. That doesn't mean you stop moving. You're still falling. You just don't accelerate. You don't speed up anymore. You stop accelerating and you go at a constant terminal velocity after that. So obviously, based off of that, terminal velocity depends on our air resistance. So the greater the air resistance, the greater our effect will be, and the lower the terminal velocity is going to be. And air resistance depends on surface area. More surface area equals lower terminal velocity. That's why we use parachutes when we jump out of a plane. When you jump out of a plane, you greatly increase your surface area, which is going to greatly decrease your terminal velocity, making it to where you can fall at a speed that is not going to kill you. So keep in mind that the longer something accelerates, the faster it's going to be going. So less surface area means it's going to accelerate for a longer time before it reaches that terminal velocity, so it's going to be going faster. More surface area means it's going to accelerate for less time before it reaches that terminal velocity. So the greater the surface area, the lower your terminal velocity is going to be. And that's basically it. Now, you're not ever going to have to actually calculate air resistance in this class, because it's mathematically too complicated for the scope of this class, but you do need to understand how air resistance does affect things. So before we go on any farther, I do want to say we are going to do an example problem in a second, but this is just going to be a kinematics problem. And kinematics and free fall are very closely related. Free fall is simply a kinematic situation. So when we look at our example problem of how high an object was going when it was dropped, well, how high the object was is our height, which is essentially our displacement. So that's what I want to know. I want to know the displacement that the object had. And it says that it was dropped from rest, which tells me that the initial velocity was 0 meters per second. And it fell for 12.6 seconds. Let me write what that actually is. That's time is 12.6 seconds. Okay? Before hitting the ground. Assume it fell in a vacuum. That's important because what that tells us is that this is a free fall situation. It's falling in a vacuum, or we're ignoring air resistance. It's a free fall situation. And anytime something is in free fall, we know that the acceleration equals little g. So the acceleration is a negative 9.8 meters per second squared. So we're going to solve this problem now. Okay, well, I know my I know my initial velocity, I know my time, I know my acceleration, and I want to know displacement. So I'm going to use the big long quadratic equation. VIT equals, plus, that's a plus sign, plus 1/2. I'm going to write a g because I know that my g is, or my acceleration is g. So 1/2 g t squared. So I know that VI is 0, so that whole term disappears. And now I just have the equation of delta D equals 1/2 g t squared. So now I need to plug in my numbers because I'm looking for my displacement. So that's going to be 1/2 a negative 9.8 times 12.6 squared. And when I put all that into my calculator, I get a delta D of negative 777.9 meters. Now, this does not actually answer the question because this tells me how far it fell. That's my displacement, how far it fell. And it's a negative displacement, which is great because it's falling down, so it should be a negative displacement. But what the question is actually asking is for how high the object was. So my displacement is negative 777.9 meters, but my height is actually a positive. It starts at a positive 777.9 meters and falls down 777.9 meters before hitting the floor. So be careful about whether the question is asking for how high something was or how far it fell. If it said how far it fell, my answer would be negative because it fell in the negative direction. But since it asked for how high it was, it's asking for its starting position, which would be a positive number. So there's free fall. That's your example problem, and hopefully you can see that a free fall, the problems are not that complicated if you look at them in terms of they're kinematics problems where I already know that the acceleration is g. That's what makes free fall awesome. So good luck on your assignment and have a good day.